Hi everyone, and welcome to a series of videos going through some past exam questions on redox titrations. This is the first of two videos looking specifically at redox titrations involving manganate ions. So if we look here, a lot of these questions have a whole bunch of information at the start. So if we just have a look, see what this is saying. So it's talking about potassium manganate can be, so these are the manganate ions that we were talking about. Potassium manganate can be prepared by a two-step synthesis from manganese 4 oxide. Okay. In step 1, manganese 4 oxide is heated strongly with potassium hydroxide and potassium chlorate, which is an oxidizing agent. Manganese 4 oxide is oxidized to manganate ions. Step 2, potassium manganate, this manganate 6 ions. So potassium manganate 6 is separated from the alkaline mixture as a green solid. In this step, potassium manganate 6 is heated in water. Manganate 6 ions disproportionate to form manganate 7 ions and a precipitate of manganese 4 oxide. Okay. Right, there's a lot of information there. Let's see what the question is actually saying. Step 1, a redox reaction takes place. Add the correct number of electrons to the correct sides of the incomplete oxidation and reduction half equations. Okay, so we need to just look at where do we need to put electrons in these. Everything else is done for us. So to work out the electrons, we need to look at the oxidation numbers. So here, this is the manganese oxide. We know that oxygen, its oxidation number is -2 usually. So if there's two of those, that adds up to -4. So the manganese here must be +4. This is our manganese 4 oxide. And then this here, we've got, again, oxygen would be -2. Times it by 4 would be -8. And so if it adds up, if it's a 2- ion, then the manganese here must be +6. So it's going from +4 to +6. So it's being oxidized. If it's being oxidized, then it's losing electrons. So the electrons are going to have to be on the right-hand side. And if it's going from 4 to 6, it must be 2 electrons. Okay, and then in the second one here, it must be the chlorine that's changing its oxidation number here, because hydrogen's always, well, almost always +1, oxygen's almost always -2. So here, 3 lots of -2 is -6, and if it's a negative ion overall, that means the chlorine must be +5. And here the chlorine is obviously -1, because that's the charge on the ion. So it's gone from +5 to -1, it's been reduced, and it's been reduced by 6. So 6 electrons, and if it's reduction, it's gaining electrons, isn't it? So it must be 6 electrons there. Okay. It then says here, in step 2, an equilibrium is set up. Okay. The equilibrium position can be shifted by bubbling carbon dioxide gas through the mixture. Suggest with the aid of an equation how the equilibrium position shifts. So this is not immediately obvious because we're adding carbon dioxide, but there's no carbon dioxide in the equation, so it's not like it's a reactant or a product. But the key thing here is that whenever we bubble carbon dioxide gas, we're putting carbon dioxide gas into water. Whenever CO2 reacts with water, it makes an acid. So this is the key sort of fact that you need to know to be able to understand this question. So the CO2 reacts with water to form carbonic acid, which is H2CO3. And this is the acid, you might have come across this before in the acids topic, because this is the acid that's part of the buffer system that's in the blood. It's a carbonic acid and hydrogen carbonate buffer solution. So when we're adding CO2, what we're really doing is adding acid. So then we've got to think about what's going to happen next. So that carbonic acid, what is that going to react with? That's going to react with the hydroxide ions, right? We've got an acid and an alkali, so these two are going to react. And it says we need to do it with the aid of an equation. So we could have written an equation for this. We could have just done CO2 plus H2O makes that would be fine. That would count as using an equation. But I'm going to write the equation here. So then the H2CO3 reacts with OH minus ions. So if we write this here. So what's going to happen here is, I mean, they always do the same thing. Hydroxide ions, it's a base, isn't it? So it's going to accept a proton from the acid. So it's going to make water and the hydrogen carbonate ion. Okay. So what we've done then is we've used up the OH minus ions. Okay. So what's going to happen then is that the equilibrium is going to shift to the right to produce the OH minus ions back again. Okay. Because remember, the equilibrium always counteracts any change that we make, right? It's Le Chatelier's principle. Whatever change you make, the equilibrium counteracts it. The change that we've made essentially is to get rid of OH minus ions by reacting them with that carbonic acid. So it's going to produce them back again. Okay. And that's going to get us our 3 marks. With 1 mark for talking about this, 1 mark for our equation, and then 1 mark for saying which way the equilibrium is going to shift. Okay, this question then continues, and we get this part of the question here. So it says, potassium manganate 7 in acidic conditions can be used in analysis. Student analyzes a sample of sodium sulfite using the following method. Dissolve 0.72 grams of sodium sulfite in water, though it's impure. So we're going to be working out the percentage purity. Okay. So if it's impure, that's what we have to work out. Make it up to 100 centimeters cubed. Titrate 25 centimeters cubed with this manganate, potassium manganate. The volume required is 26.2. Here's the equation. Okay. So the first thing we want to do in any of these types of calculations is always work out the number of moles. So what do we know? We know that we've got the potassium manganate, we know its volume, and we know its concentration. So this is where we're going to start. So we're going to do 26.2 over 1,000. That'll get it into decimeters cubed, and we'll times that by the concentration. Let's work this out. So it's 26.2 divided by 1,000 times 0.02. So we get 5.24 times 10 to the minus 4, and that is the moles of the potassium manganate. Okay, so where do we go from here then? Now we've got the moles of one of our species. We then want to use the equation to find the ratio. So we want to know about the sodium sulfite. So we're interested in the sulfite ions here. So we're going to look at the equation. So if we say from the equation, if we look at the ratio of these things, so the ratio of MnO4 minus to the sulfite ion that we're interested in is 2 to 5. So what we're going to do then is take this, divide it by 2, and then times it by 5. Okay, so we're going to divide by 2, and we're going to times by 5. And so we get 1.31 times 10 to the minus 3 moles of the sulfite ion. Right, so where are we? Let's go back and look at our question. We've used this number, we've used this, we calculated those. So what we now need to look at, this is a useful trick I often do, is just go and look through all the numbers. Usually you have to use every number in the question. They don't tend to give you information that's useless. So let's just do a check. We haven't done anything with these volumes. Right, this matters because this was 25 centimeters cubed, but the original solution was 100 centimeters cubed. Okay, so we're going to need to get the moles in the original 100 centimeters cubed, we're going to need to times this by 4. Okay. Let's just do that. So it's 5.24 times 10 to the minus 3 moles of sulfite in the original 100 centimeters cubed. That matters because that's the solution that the 0.72 grams was dissolved in. Okay, so we need to know the number of moles in that solution. And then, so that's done our volume. So now all we've got left here is the mass to use. So what we want is to calculate the mass and then do it as a percentage. So if we've got moles, we now need to times this by the formula mass to get the mass. So we want the MR of the sodium sulfite. So we want to use the sodium sulfite, right? Not just the sulfite ion. So we want to use Na2SO3. So it's going to be 23 times 2. You look these up on your periodic table, right? Sulfur is 32.1. Let's work that out. So 23 times 2 plus 32.1 plus 16 times 3. It's 126.1. So now we can multiply that by our number of moles from here. And that will give us the mass. So we're going to times by 5.24 times 10 to the minus 3. And we get 0.66 grams-ish. You can see them with more decimal places there. And so now I'm going to do this as a percentage of the 0.72 grams that we had at the start, and that'll give us the purity. But I'm going to use the whole number on the calculator, even though I've just written that down. I'm going to use this whole number. And we don't want to round anything until we get to the very end. Divided by 0.72. And we've got 91.77%. Does it say? It doesn't say anywhere in the question about how many significant figures we need to do this to. So I don't think they're going to mark us down for this one. So we should be fine. So we're going to call this 91.77. That's fine. Okay.